Learn Efficient Pharmacology, Pharmacokinetics, Part 8, Phases of Drug Metabolism. To understand the phases of drug metabolism, let's revisit the metabolism of phenytoin we saw earlier. In phase 1, a hydroxyl group was introduced, and then in phase 2, a glucuronic acid moiety is conjugated with it. Here, the newly introduced hydroxyl group provided an oxygen atom that acts as an acceptor site for the glucuronic acid moiety. In a xenobiotic molecule, in addition to oxygen, nitrogen or sulfur atoms can also act as acceptor sites. Such acceptor sites can be introduced or unmasked by many reactions other than hydroxylations too. We have listed a few major reactions here. Pause the video to view those. If you look closely, the importance of oxygen as a substrate is obvious. How was oxygen introduced into these reactions? By a moiety that can bind to oxygen. Can you guess what that is? It is heme. We know that in the red blood cells, heme within hemoglobin binds to oxygen. Similarly, in the hepatocyte, heme within the xenobiotic metabolizing enzymes also bind to oxygen. Now, heme is a colored pigment. The Greek word for color is chroma, and the cell is denoted by cyto. So, this colored enzyme within the cell is called cytochrome. One family of such enzymes is the cytochrome P450 or CYP. CYPs mediate the phase 1 metabolism of a large fraction of drugs used in clinical practice. Where do you think these CYPs are located in the cell? Once a lipid-soluble xenobiotic enters the cell, it tends to accumulate in the lipid bilayer of the endoplasmic reticulum. So, if the substrate is within the lipid bilayer of the endoplasmic reticulum, it makes perfect sense for the CYPs to be attached to the same lipid bilayer. The fragments of endoplasmic reticulum, when isolated in the laboratory, form closed vesicles called the microsomes. So, the enzymes embedded within the endoplasmic reticulum are also called microsomal enzymes. A functional group can also be introduced or unmasked without involving the CYPs, that is, in a CYP-independent reaction. For example, a water molecule can break the chemical bonds in a xenobiotic. This is hydrolysis. Depending on the bond that is broken, this may be an amide, ester, or epoxide hydrolysis. The enzymes involved are carboxyl esterases and epoxide hydrolases. So now we have CYP-mediated oxidation and CYP-independent hydrolysis. There are also other phase 1 reactions that are minor contributors to drug metabolism. Pause the video to view these. In phase 1, a functional group is introduced or unmasked. So, phase 1 reactions are also called functionalization reactions. This functionalization is in preparation for the phase 2 metabolism. Phase 1 generally inactivates the xenobiotic. The water solubility, though, is only slightly increased. It is phase 2 that results in a metabolite that is highly water soluble. For this, a water-loving or hydrophilic moiety like glucuronic acid, glutathione, or functional groups like methyl, acetyl, or sulfate is conjugated to or transferred onto the xenobiotic. The enzymes that mediate this transfer are called transferases. The conjugate formed is highly water soluble. It can dissolve in urine, bile, or other body fluids and is easily excreted. The site of conjugation reactions is based on the location of the enzymes within the cell. Glucuronosyl transferase is a microsomal enzyme, so glucuronidation occurs in the endoplasmic reticulum. Other phase 2 enzymes are mostly cytosolic. But a major challenge is that over a lifetime, the human body is exposed to more than 1 million xenobiotics. Can you guess how this is addressed? We shall see that in the next video. Here are some good to know facts. This is a summary of our discussion.